Okay, welcome. It's a lecture 5, session 1 of the artificial intelligence class. Hope I am audible. Can anybody please confirm once again? I am audible. Am I audible? Okay, thank you very much. So today we are going to see a very important topic that is actually related to the problem solving, and this is in continuation with the whatever we have done in the last class, and then therefore let us start. Okay. In the last class we have seen various strategies for finding the solution, and we have seen that there is something called state space. What is the state space? Means in all the states that are possible when you start from one place to another, such as if you want to play a game of chess, all board position they contribute as a state space. So you can say that if you are into one state, then you can draw a line. Now, assume it as a graph that lot of nodes are there. Every node is a state. So if you are into one state, you can take some move, and after taking that move, you go to the another state. So in this way, you can realize a graph, and then finding out the solution means if you are at the starting board position, then going to the winning board position is a place everywhere where the place where there is no king of the opponent, you want to reach at that place. So you apply some strategies, and those strategies are called the search strategies. So we have seen that from very basic point of view, you can apply DFS, depth first search, or breadth first search. In the last class, we have also assumed that there could be other strategies also, and we also had a running example in the last class. That is, there was a map of Romania, and where a agent want to go from a place called Arad to the Bucharest, and this was a very important thing. So we have seen that two kind of approaches, two broad categories of approaches we can apply. One broad category is this, that you don't know anything about any other information about the system. You only know that these are the nodes, and these are the distances between them. Means the map is only given to you, and then you try to find out the solution. And second could be that when some other information is also available, and that is you can consider as a hidden information that is provided to you, and we call it heuristic information. So when no more information is available, only the problem definition is given to you, then it is called the blind search strategies we have discussed in the last class. And after blind search strategies, when some information is given to you, then it's a heuristic search strategies. So in the last class we have seen a heuristic search strategy that is called A star search, and we have although discussed some part of this. So today we are going to see this particular algorithm in more detail. So let's first see that how the algorithm works. Okay. So the algorithm works in this way, that at any node it try to use this particular formula Fn and Gn. Fn is equal to Gn plus Hn. So these two things it is going to use to proceed further. What does it mean? What is the Gn and what is Hn? Can you recall this particular thing? Okay, or should I explain? Okay, do you know what is Gn and Fn, or should I explain? Okay, if you are not writing, I would assume that you understand these things. Okay, so let's assume that there is these are the nodes, state space nodes, and there is some connection between them, and the user and the system want to take a move. Let's assume that these are the nodes, and there is some connection, and every connection has some weight. Okay, weight associated. And let me just quickly draw something. Let's assume that this is the graph. This is the graph that you have, and there are some places. Let's say this is 3 unit, this is 5 unit, this is 6 unit, this is 2 unit, 3 unit, 1 unit, 1 unit, 5 unit, 3 unit, 2. Let me just write some number, okay, so that it becomes easy for you to decide that what should be. My question is that what should be the right way to let me ask this question, that if you start from this particular node, if this is the start node, okay, and you want to reach this particular place, this is called the goal node here. So if you want to start from this node and want to go to this node, how would you proceed? Okay, so there are two things into the informed search strategies. Some heuristic function is given to you, and heuristic function provides some extra information about the problem. And let this, as it is required, I would give you that what this information is. So let's assume when you are here, the information, this H information says that what is the air distance between the goal state and the state in which you are in. Okay, let me also just sake of completeness, let me just also write this is the N1, node 1 and node 2, node 3, node 4, node 5, node 6, node 7, node 8, node 9, node 10, node 11, node 12. The goal is node 12. So let's assume when you are into the N1, so H of N1 tells you that what is the air distance between the N1 and the H12. It would be 1000 kilometers. Okay, let's assume be 1000 kilometers. Okay, yeah, let's assume for the sake of simplicity, let me just say this small numbers would be better. Let me just take it 10. Okay, let me take it 10. So at this state, what is your GN? Let me also talk about the GN. What is GN? The GN gives you for any node that how much distance you have traveled from the starting node. Okay, so if I ask G of N1, then what will the answer? 0, because you have not traveled any distance. अभी तक तो कुछ नहीं चला. You are at the start node only. So GN1 is 0, and then you would try to see what is nearby you. So from N1 you see 3 candidates, and those candidates are, can anybody tell? N4, N2 and N5. Those candidates are N4, N2 and N5. Are you with me? Because from N1 you see that you can go to the N2, go to the N5 and go to the N4. No other way. So let me just write here also 3. Okay. So can you tell me that if you go to the N5, let's consider N4. Okay. If you go to the N4, how much distance you have traveled? 7. Okay. If you go to the N2, how much distance you have traveled? N2 distance is 3. If you go to the N5, how much distance you have traveled? N5, it is 7. Are you with me? Everybody sees this? Can see this? Then another information is needed. What is the H value of N4? What is the H value of N2? What is H value of N5? Okay. And this information, I am telling you that this information is coming from some other source. This is not directly given to you. It is coming from some other source. And let's assume that this information is like this. Say it is 6, 5, 4. I don't know how I have arrived at this. Then you are going to use these numbers. Yes, 4, 7 plus 6. H2, 3 plus 5. And 5, 7 plus 4. Do you understand? At every node, then you see that what is the summation? Summation is 13. Here the summation 8. Here the summation is 11. So which node you are going to select to forward? Because all these things are your candidate. But which one you are going to select? You are going to select the one which is going to cost you lesser, and that particular node is H8. So you understood this thing? That what is the two things? Two things you should understand. One part is that whenever you have arrived at this particular node, say N2, whenever you have arrived at this particular node N2, you have actually traveled this particular distance. First part is that you have traveled something. That is called the GN. Another thing and this is the first part, GN part, and another part is the heuristic. That is somebody else is telling you that what is remaining, means how much more effort is needed if you go from this place to another. It could be a, as I'm telling that it is a distance, and somebody told you that it's 5. So you are going to use this 5 plus 3, and therefore the summation is 8. And similarly, you find out for other nodes also. And when you see that the minimum value is 8, so from here, your frontier is going to be forwarded to this particular node. And from this node, again you are going to see that which is a better for me. And here you would be seeing what are the possibilities: H4, H3, and H8. Again, you would be considering those things and try to see that which have this particular which have the minimum value for these combinations. Are you with me? So this is the important part. So number one part is this. Okay, let's just go back. Okay, so this A star algorithm uses this particular function fn is equal to gn plus hn to select the next one to be explored. Okay. Okay. This particular algorithm is both optimal and complete. You know what is optimal means? Optimal means that it tries to give you the path that takes the minimum, that minimizes some value. And here what I need to minimize? I need to minimize the distance. So therefore, it optimizes, means minimizes or maximizes some value. Complete means, what is the meaning of A star is complete? Complete means, we have discussed in the last class, that an algorithm is complete means if there exists a solution, the algorithm would give you that solution. So there is a very important property that optimal, since Gn is given the, okay. So this we have discussed that optimality comes because of this particular heuristic function. And heuristic function, there is a property, there is a very important thing. What is the heuristic function? We have already talked in the last class. And once again, I want to emphasize on this, that this particular HN, that is the hidden information that is provided to you. What information is he provides to you? It provides you the information that what is the remaining cost going to be. Okay, so most of the time, this particular value is in such a way that it is, look, nobody can give you the exact estimate. Okay, it would be a kind of estimated value that is going to that you are going to spend from that particular node onwards. So, and that particular estimate would not overshoot the actual value. This is only the property this particular function has. What property this particular heuristic function has? That it tries to estimate the cost of the cheapest solution through n, because what is the solution way forward? But this solution, whatever value it is going to give, it is actually lesser than the actual solution. So actual solution may cost you more. So therefore, it's a lower bound, means it is never overshoot the value that is that you are going to spend. Are you with me? Can you understand this fact? Since Gn gives the path cost from the start node to the end, and the Hn is the estimated cost. Look, this is the information. Hn is the estimated cost of the cheapest path from the node end to the goal. Okay. So there is two important property. One is this particular property that it is never going to over estimate, means whatever value Hn is going to give you, it is lesser than the actual cost that it is going to be on you, on your algorithm. Number one thing, this is called the admissibility property. Another property is the consistency property. And what is the consistency property? Consistency property, or it is also called the monotonicity property. It says that this particular formulation. And what is this formulation? That it tells this particular thing. That let's assume that there is some graph where there is node and there is some end node and there is some connections are there. Okay, in between, let's assume that I am here, and this is the node n, and this is the next node, that is n dash node, some other node, I'm not telling that this particular node. Then you can see that what the h of n is going to represent, what the h of n is going to give you. H of n is going to give you estimated distance from here to here. Okay, hn is going to give you this value. What is hn dash is going to give you? Hn dash estimated distance from n dash node n dash to the goal state. Okay, so it tells you that if hn is some value and hn dash is some other value, so you can sometime, if this value is smaller, so you may be tempted that it is better that you go from n to n dash and then you take this route and you come back here. So let that cost is, I don't know what is the cost, let me just represent n to n dash. If you go from n to n taking some action, say a, and this is the extra cost that you are going to give. Okay, so if you are so overall, if from n to this goal state, there is two ways that you can go. Either you can go directly, and then it is using heuristic function says that this much you have to pay. Another way, that from n to you go to n dash, this is some cost, and then from there you take the direct route. That is this thing. This thing is given by this heuristic function. So if you take this second route, so it should not be the smaller route, because you when you are at the some node, then it should be the smallest node. So this is the condition. Okay, the condition is this, that if you take a smaller node from any other place, that place should cost you more. If you are going to some other node, then that that should cost you more. Can you understand this? Can anybody write yes? Do you understand this? Can anybody write yes? Okay. It is very straightforward. It is very straightforward. Just let me tell you once again that you are at this node. You want to go over here. There are two ways. Number one, that you go from n to goal. Second way is you go from n to n dash, and then you go for n dash to goal. Okay. So it says that if you are going into the second route, it should not be cheaper. So this is what the cost for the second route. This is cost for the second route. How? From n to n dash, this much is the cost. From n dash to goal, this is the cost, because the h function directly gives you the cost. If you find out the summation, that should be at least that much. Means it should not be lesser than the cost that is going from the route 1. This is what it is. And this is a very important property. We have this is a new thing we have not discussed in the last class, that consistency is a property, and consistency or monotonicity, this property actually says that whenever you are going to take an alternate way, it is not going to be cheaper in terms of the h. It is not going to cheaper in terms of the h. This h function, whatever the value h function provides, it would not be cheaper. And also because of these properties, if these two properties, what are the two properties? Number one, admissibility means the optimal, the admissibility means this function never overestimate, means whatever the actual value is, it don't say that it don't give you the value greater than that. Number one, the admissibility property and the consistency property. If these two properties are there, then A star function is going to give you the optimal and complete solution, and it is guaranteed that no other optimal algorithm is guaranteed to expand fewer number of nodes than the A star. Very important and impressive algorithm in front of you. So let us just see that how this algorithm works, and this is, I think we should be quick in that. So the same thing I want to do. You know that this is the map of Romania that we have seen multiple number of times. Let somebody provide you this heuristic, that what is the distance to the Bucharest from Arad, from Mehadia, and similarly many places. Bucharest, the distance is 0, and Niam, the distance is 234. Similarly, all these values are heuristic values are provided to you. So from initially when you start, you just try to see that what is the value of Bucharest, because from Arad you see that the distance is 366. So 366 for 0, two functions you are going to add. So therefore there is no way. Arad you have to only expand because it is the only node available into the frontier. Then when you expand the array, you see array, you find Zerind, CBU, and Timonosa. These three places you find out and see the distance is 75, 140, and 118 direct distance. You find out, you write them 140, 75, and 140, 118, and 75, and you add them with the air distance that is available over. For Zerind, you see the what is the distance? Can you find out? Zerind is 374. So therefore, 374 plus 75. 374 plus 75 becomes 374. Okay. So similarly, you can find out the summation over here. These two items are you can find out, and then you see where is the minimum value. This value is 393, then 447, then 449. The minimum is CBU. So you are going to explode the CBU. So when CBU, you will explode these values to you see how many places are there from CBU. 4 places. 1, 2, 3, 4. Other than or idea both are places are available from CBU. You can go at the 4 places. For all those places, you find out what is the distance. You see that from Arad it is to, again, because you see the Arad is again expanded 366, and you find out the same value 646 and 415. How come it becomes 466? Because it says that how much you have spent till going Arad. So when you is from Sibowi, if you go to the Arad, it is going to be the 140 plus 140 because you are going to returning over there, and then from Arad. The value is 366, so it is 240 plus 366. So similarly, you can find out that these are the values. So these are the values. So out of them, you see the minimum is 413. You expand that, and you find out new values. And then you saw that whatever new values you have expanded, out of them, because all these things go into all these. Whenever you expand a new node, you send that into frontier. And the frontier is going to be a priority list where the values are sorted based on the values. And what are these values? These values are this summation, this F value. So these, if you sort them based on the F value, you see that these values of 417 and 357 and 526 becomes larger, and the minimum value would be corresponding to the Figueres, that is 415. Now you are going to expand that thing. Here you find out the Cebu and Bucharest, and since you find out the Bucharest, you are going to stop at this moment. Then again you see 450, then you find out 417 also. Although you have expounded the Bucharest here, you find out there could be another small route available. You see then because Bucharest, when they are expanded, they will be put into the frontier, and from the frontier which node comes out? The node comes out is going to be 417 because these are the on values now. 447, 449, 553, 417, 526, 450, 491. So you see the minimum is 471. But when you expand that, all these value 418, 418, and 615 and 614. And here you find out the Bucharest once again, and this Bucharest has a smaller value than the previous one, so therefore you find out this particular route from Arad, Cebu, and then this particular route. So I think this algorithm should be clear, and how this algorithm is expanding the nodes. Are you with me? Can anybody write that it is clear? Okay, is it clear? Okay. Can anybody please confirm that you understand this algorithm, A-star algorithm? Look, things are very simple. Number one, you find out whenever you are expanding the nodes, where you are going to put into those nodes, you are going to put those nodes into the frontier. Frontier is actually sort based on a value, and that value is this particular F value, and F value is the summation of H and G. Those two things means how much distance you have came and what is expected that you are going to spend. So this summation, if this summation is minimum from some node, that node is going to be extracted first. This is how we are going to proceed. Okay. Okay, so we have seen this algorithm. Now we would talk about the optimality of the A-star algorithm. What do we mean by optimality? That if there is some other path available that takes lesser expense, this particular algorithm would only follow that path. So you see that one example over here, that here the Bucharest was, although it has been discovered, but this route has not been chosen. Another route has been chosen that has the value 418 as compared to 450 here. Okay, so how this can be proved, we know. Okay, this thing. Okay, this thing we have seen recently, that if there is you are at the node H and there is some other node N, and you are at the node N and there is some other node N dash. So this thing happens, means you have at least you are going to spend that much. That is, if you are changing the route, you are going to spend more. At least the minimum would be that you are going to spend whatever here, the same thing you are going to spend. It can only cost you larger, it cannot cost you lesser. This we know. So let us see that what is the F value when you go at the different node. So when you are F and S, what is the F and S? This is the general formulation. You know that and that node you find out what is the G value and what is the H value. So on that node you find out this. Okay. So let me just go back here. Okay. So you see this. Okay. So what I was telling this, that let's assume that there is a node N and there is a node N dash and there is a goal node. Okay. So what is F and dash? F and dash is the estimation that how much you are going to spend into this particular way. And we know that this actually has two parts. Fn is that how much you have spent over here, that is G and dash, plus that what is expected that you are going to spend over here. Okay, that is H and dash. Okay, so this we know that if this H and dash and F and dash, these are the two parts that you are going to have. What is the value of G and dash? What is the value of G and dash? It may be possible that it could also be possible that you from somewhere you came to this node and then you went to this node. Okay, so you can write it like that, you can say that this is Gn, this is G of n, because somewhere you came to this place and that would cost you Gn, and then you are going to spend this much from here. How much it is? It is plus cost of going from n to n dash by taking some action A. Okay, and from here onwards it is you are going to spend this much, that is H of n dash. Okay, and we know that this particular thing has a special meaning. Okay, what it is? We have seen that this particular thing we have what is in terms of Hn, you can say Hn is less than this value. Okay, Hn is less than or equal to this value. So if in this place you want to put a smaller value, if I remove this thing and I put Hn, then overall expression is going to be smaller. Okay, so I can say that this overall value is going to be smaller. So let us go back to the presentation. The same thing is shown over here. So you see that this G and dash becomes Gn and the cost of this, and then the overall value becomes smaller. If you remove these two terms and you put Hn over there, so the overall value becomes small. And you know that these two values summation is going to be Fn. Okay, this is going to be Fn. What does it mean? It means that Fn dash is smaller than Fn. Okay, you got this idea? This was you understand now? So I say that Fn and then I wrote something else, that Gn plus Hn, and this Gn plus Hn I have written Fn. Okay, it becomes smaller. Fn dash, okay, is greater than Fn. Okay, the value of S is not decreasing along the path. Okay, the value of F is not decreasing along the path. What is f? F is a summation. So therefore, whenever you are going forward, your f value is going to increase. H value is going to decrease, but f value is going to increase. Okay, and also you see this thing. If f value is going to increase, it is not going to decrease. Then you know that there is some optimal value, because f at the end h value for the goal is going to be 0. H value for the goal is going to be 0, and then overall summation is going to be summation is going to be only the gn part, and that tells that how much you have spent from coming from the source to this particular place, and that is, since being minimal, it is going to be the smallest value. So one thing you see that this value is there is some value that starts with some value and only grows, and then you see one more thing. A star expands nodes in order of optimal path. It only sees the things into the optimal distance. Okay, one by one, it is incremental only, and incremental means when it expands something, there is nothing less, nothing shorter path available. Whenever it expands some path, there is no other shorter path available. So let's assume on the contradiction that nahi aisa nahi hai, it's not like that. Let's assume that no, there is some other shorter path available, but this algorithm has taken another path, and therefore my things are not optimal. So why it has happened? Why it could happen? It could only happen that in the frontier there is another. I have selected a node n, but there is some another node is available in the frontier. Okay, that has a smaller value. It is only possible because if there is some another node available into the frontier who has f value smaller, but I have chosen larger value. But it is not possible because it is not possible because the algorithm forwards in this way that it in every step it chooses only the smaller value, available value, smallest available value. So therefore, this algorithm is optimal. If we think that this algorithm is not optimal, if we assume that this algorithm is not optimal, then we arise to a contradiction. So therefore, this gives the proof for the optimality of the A star algorithm. Can you understand this? Okay. Okay. So let us also talk about the completeness. Means if the solution exists, this algorithm would give you the solution. Okay. How can we prove that if the solution exists, this algorithm would give you that solution? This is what is called the completeness of the algorithm. Okay. So to prove this, we are going to use this fact that f is not decreasing. Okay, you know that initially you have some f value, and it was initially 380. Say what is the 380 value, and then when you forwarded to another node, the value increased. Then you forwarded to another place, the value increased. Are you able to see this? Are you able to see this? Are you with me that f value is non-decreasing? The fact that f value is non-decreasing. How we had proved? We have proved using this proof. This proof proved that f value is non-decreasing. It's only increasing. And we have seen earlier into this example, into this graph, that f value was 360, then 393, then 413, then we have chosen this 409, 314, then 413 we go 415, and from 415 we went, what is the next one? This one, huh? This one to be exported. 415 it went to the 4, which one? From 415 here it 417. Okay, it has expanded 417 and then 418. So one by one it is increasing. You see all these values. Just let me take this value, take it to here. This just write that what are these values. These values you can see the f value. Just I am going to give you the example also. You just see from example. Initially it was 366 here. Then we went here where it become 393. Then we came here, that is 413. and we came here 413. Then we expanded here 415. Then we went here, that is 417, and then at the end when we find out the solution, it was 418. 418. So you see that all these values are increasing only. Okay. So what does it mean? It means this. It means that if you are on some node, if you are here, okay, and you have some value, say x, okay, then you are considering some node. I'm not going to write. You are considering some other node. Then your value increases. So initially you are here, say some value is x. So let's inside this place all the values are x. Then you got x plus value. Okay, because when you consider this node, your value you have forwarded to this. Now your value has increased, and if you are inside searching, then your value is not going to be greater than this x plus. Okay, then another value there would, when your value increases, then you can find out that there would be some node that would be having the value. If you go to those nodes, the value f value would be equal to the say x plus plus. So you see that one by one, when you consider more node, when your value is increasing, there are only few number of new nodes are added. Then let's assume that here is your solution. So you can see that this at some point of time, this particular contour would cover that particular goal node also. Okay, and let's assume at the goal the value is y. So how much you need to increment? You only need to increment from y minus x. If everything increments, at least its smallest value of increment is going to be epsilon, I mean there will be some threshold, because if it is an integer, the minimum value would be 1. In case every step is going to take say 10, then epsilon value would be 10. So at least these many number of steps is required. Okay, if you start from x and you reach to the y, what is the value? F value you start from x, initial f value was x, and when you reach to the goal, your f value becomes y. Then you have gained y minus x, then you have gained y minus x, and if in every step minimum increase is epsilon, therefore in these many number of steps you would be able to reach to the goal state. And this number is going to be finite only. And if this number is going to be finite, this algorithm is going to give you the result. Are you able to see this? So the completeness means this, if the solution exists, this algorithm would give you the solution, is based on these facts that there is a area where the value f value would be lesser than some pre-specified value, such as here 380, only one node. In 400, these two nodes would be there. In 420, you can see that these nodes comes into the 420, and Bucharest comes over there. The progress through the contour crossing, if we think that the algorithm when evaluate all the nodes over here, because you can see that nodes would be here, if we evaluate all the nodes, then after that it would come out. When it come out, then it would evaluate these nodes, and there would be, and then if you go through in this way, it is expected that in finite number of steps you would be able to reach the goal state. What is the error? There are two kind of error, you know that. Okay, but the problem is, look here also there could be only one problem, that it is expected to have the infinite many nodes in each contour, and if there are infinitely many items over here, then we could be in problem. But otherwise, we expect that the solution would be provided. Okay. What is the time complexity of Is Zc444 algorithm? It is order of b to the power epsilon d, where d is the solution depth. Let me tell you that what this value is. B is the solution depth. So let you assume that in the tree you go how many steps you travel. D is the solution depth. It is very high and makes A star algorithm impractical. And this is the most important crucial problem with this. Although it looks like that it can solve all the problems, but this is the most important problem. That time complexity is b to the power epsilon d. What is epsilon? Okay, what is epsilon? Epsilon is the part that I told you that it is a minimum increment that is required. Okay, if it could be 1, if it is sometime it could be 1 or other number. The branching factor which actually multiplied with this factor b to the power epsilon d. So this is what it is. Okay, so these are the two proofs that are important. So we have seen the problem. One very important big problem over here, that this algorithm takes lot of time. Okay, the time taken by this algorithm is very high. So how to counter with that? That memory requirement of the A star could be reduced using the iterative deepening. Okay, so what is iterative deepening? Earlier we have also seen that in the DFS algorithm actually was not going to give you the solution if they are infinite, if the depth is infinite. We have seen earlier that DFS algorithm is, you know that the BFS would give you the solution, but DFS would not give you the solution. You remember that part? Let me just tell you one thing. Let's assume you start from here. So BFS says that you see that what are the branching other items are there. Then you branching factor is B. So you from first item you go to these items from first item, and you saw the similar structure would be there. Means there would be next items, would be next item, then there would be next item, next item, next item. Okay, a lot of items are there. So let's assume the condition that there are infinitely, the depth is infinite, and also we should think that there is somewhere there is a goal. Okay, okay. So what is the strategy of DFS? Okay, DFS. Let us first see BFS, breadth first search. Okay, breadth first search. First evaluate this node, then this, then this, then this, then this, and then this, then this, then this. Somehow it reaches to this particular goal state. Understand? What happened with the DFS, depth first search? It tried to finish all the things into one line. So from here it goes to here, from here, then here, then here, then here, then here, then here. It goes away. And as I'm telling that the depth is infinite, what is going to happen? Solution is here, but it would not be able to find out the solution. So can you see this? Similar thing is applied over here. The similar problem is here, that to come similar kind of things you can apply. So एक चीज और one more thing I want to tell, that how to solve this particular problem. We have seen that to solve this thing, you say that I would not go beyond the say depth k. I would not go beyond the depth k. Okay, so what would happen this time? You let k is equal to 2. So you from here you come here, from here you go here, but after that you would not go. You would come back, and from here you will come back and you try to see this thing and try to see this thing, and you will only see this, and you will say the answer is not there. Then I would make k is equal to 3. Then you would search till this point. Then I would say k is equal to 4. Then you would search till this point and you would find out the solution. So this is called the iterative deepening. We have seen this in the last class. So similar thing we have to apply over here. IDA star algorithm. Here it uses cutoff based on the far. Please tell. Somebody is asking, sir, please tell when we cannot use BFS technique. Okay. So no, BFS we can, as I'm telling that BFS and DFS in terms of, we are seeing that the DFS has a problem. BFS don't have this kind of problem. So BFS is a better algorithm in that term. Okay. BFS is always you can apply, but DFS may have some problems. Okay. So Somebody is asking how A star work in this example. Look, A star algorithm, if you see this algorithm, how this algorithm is progressing. If you see this algorithm, let me just go back and show you this. That you can hear how this algorithm is going from where it has expanded CPU, then one place, then another place, then another place. So it somehow, don't you get a feeling that it is taking the item as a into the DFS kind of thing? Because although the items are taken into different order, they are not strictly taken because into the DFS this item then then again the same. Means DFS would go only extreme left item taking extreme left item, it will go till the end. But in the A star, given this H function, you are actually changing this order. So at some place you are actually using a different kind of item and you are following a different path. Okay, but it looks like that the same kind of problem is going to appear over here because it is going into the depth. If you are going into the depth and depth is infinite, you are going to again caught into the trap. To come out from this trap, this particular strategy would be helpful. And what is the strategy? This is the IDA star algorithm that tells that you should use a cutoff on F. You say that I would just traverse till the F value of some F value, say 500. You go to that depth and you come back. You say that item, I was not able to find out the item. And then you increase the F value. And then again you run multiple number of time. In the last example, in the last class, we have discussed that sometimes you feel that if iteratively I am applying this algorithm many of the time, as I told you here, you may think that if I apply this thing, if I apply second thing, if I apply third time, DFS third time, then in the third time, all these items are again expanded, all these items are again seen. If I apply fourth time, so this particular inner circle part has been actually explored 4 number of times. So you may think that this is a very bad strategy, but the point is it is not a bad strategy because most of the items are here. If you want to compare that how many items are here and here, you see that the most of the item would be actually below the tree. Maybe this number is very high. You just see that whenever even into the binary tree, you see that this is the first item, then there are 2 items, then there are 4 items, then there are 8 items. Okay, in the binary tree, then there are 8 items. You see 1 item, 2 item, 4 item, 8 item, then there are 16 items, then 32 items. And do you know what is the relationship? This 32 is 16. 16 is the double of the 16, and this 2 item is the double of the first item. This 4 item is the double of the 2 items. What does it mean? Means when this single line is containing all the items. If you find out the summation of all these things, the next line is going to be containing all these items plus 1 more item. So if this particular line you consider the next line, it contains all these items, these many number of items. Because I just want to tell you this thing. This fact, just try to find out that if I say that this is 32, now in this line this is 32, and you just find out the summation of 16 plus 8 plus 4 plus 2 plus 1. What is the summation? Can anybody tell? Can anybody tell this summation? This summation is going to be 31. Is it like that? Okay. So lot of the items are at the leaf location. So therefore, iterative deepening looks like that it is going to take lot of, it is going to do the lot of repetitive things, but actually it is not, because most of the items are at the leaf. Okay. So this is one strategy that to ask the star to finish, you are going to increase the 1 by 1 F value, and then you are telling item not found, item not found. At some point you will be seeing the item has been found. So next there is one more algorithm, that is recursive best first search, RBFS, but we are going to take a break at this moment and then we'll come back and we'll continue with this algorithm. If you have any questions, please let me know, because that would be better, because I think It's a 50-minute slot, so let me just take a break.